All right. The study of group rings has been keeping Professor Passi and others also busy for many decades. He has contributed significantly by investigating algebraic structure from various aspects. While some results give us information about the structure of these group rings, the other acquaint us with the properties of elements in this. In fact, almost each work initiated by him has created a new line of research. So I begin with a fascinating group ring, which is fascinating for me. This is a group of collaborators of Professor Passi who has worked with him, and the ring is in fact domain of his work. This is ever increasing group ring according to me, and I wish it increases even more. But because the theme of this conference is not this group ring, adhering to the theme of conference, I will now be talking of the algebraic structure group ring. G for us is a finite group, a group, and R is always a commutative group with unity. Sorry. So RG, as we all are familiar with, is a group ring which contains elements which are formal linear sums with elements from group G, and the coefficient ring is R. The augmentation homomorphism is simply a linear extension of the trivial map that we have, G going to 1. So the kernel of this homomorphism we call as augmentation ideal. And in case R is Z, which is going to be for most of the cases, we are just going to denote it by delta. All right. So firstly, like Professor Varmani, I apologize for all kind of work that could not be included in this talk owing to the time limit and massive work which goes to his credit. But the broad themes that I want to talk about, they are going to be as here. So firstly, I'll talk of the augmentation ideals and dimension subgroups, which has been topic of interest, most interest to him, at least the numbers say so. And Professor Varmani has already acquainted us with the basic notions of these and some of the important results in this direction. Then we'll talk of the algebraic elements of group algebra, where we learn about celebrated Passi-Passmann inequality. Then we talk about the Jordan decomposition property in algebra. Then he has also contributed to the structure of group algebras. There onwards, we see his contribution towards understanding the unit group of these group rings, particularly the hyperbolic unit groups, the cut groups, about which we have already seen in one of the previous talks, and also on the central series of unit groups of integral group ring, both upper and the lower central series associated. All right, so I begin by discussing few results, or this is not going to be a complete exhaustive kind of thing, so I'll just give a brief overview of the things which have been worked upon. So if G is a group, then we have this descending central series D and G, which comprises of all those elements in G such that G minus 1 enters in nth power of the augmentation ideal. These subgroups are called as dimension subgroups, and so these are the basic results that we have seen in the previous talk as well, that D and G always contains gamma and G. Gamma and G denotes the nth term of the lower central series, and the equality holds for the cases when n is less than equal to 3. It was Rips who first constructed a nilpotent 2 group of class 3 having non-trivial fourth dimensional subgroup. But then in this direction, so naturally one demands the understanding of the quotient Dn mod gamma n, which is not trivial in general, right? This is called as dimension quotient of G, and evaluation of dimension subgroups and dimension quotients is a challenging problem in the theory of group rings. And it's not a recent thing, this has been going on since 1935. Professor Passi has made immense contribution in this direction. To mention one, he has proved that for finite P groups, D4G equals gamma 4G, or n equals 4, the equality holds for this class of groups. And in this direction, in his recent developments, he gave new outlook to the topic by extending its domain and generalizing the concept. So from dimension subgroups, we have analogous concepts for Lie rings. We have the concept of relative dimension subgroups. We have the concept of generalized dimension subgroups. I will not go into the details, but then just to see an analogy which is going between the two cases, if you see for a Lie ring L, delta n, so this is analogous to Dn that we had for group. This is defined to be L intersection delta n of L, this being the augmentation ideal of enveloping, universal enveloping algebra UL, which is generated by L. And for this, for Lie ring L, we have similar result that we had for the groups. That is, delta n is equal to gamma n, the lower central series, if n is less than equal to 3, but may differ at n equals 4. For metabelian Lie ring, twice of delta n is contained in the gamma n of L, and this is the best bound has been claimed in the paper. The collaborators who have worked in this direction, you can see with each slide, you can see them listed over there. All right, one of the recent concepts is of the generalized dimension subgroups, where for any two-sided ideal of this integral group ring, he defines generalized dimension subgroup as the group elements G which lie inside, which lie in this ideal, in this 1 plus ideal A, and this G denotes the augmentation ideal that we earlier denoted by delta. In his work, he has identified this generalized dimension subgroup for various two-sided ideals in a free group ring ZF. So moving on from G, which was an arbitrary group, this is for a free group that this work was there. And he has exhibited how some of the generalized dimension subgroups are related to derived functors. He also introduced notion of relative dimension subgroups. So if n is a normal subgroup of E, I'm sorry, I have not mentioned. Okay, so if n is a normal subgroup and n is a positive integer, then the nth dimension subgroup of E relative to this normal subgroup n is given by this intersection, which is how we define relative dimension subgroups. Many theorems concerning relative dimension subgroups are proven, and it is expected that this approach will initiate further work leading to deeper understanding of subgroups determined by ideals and group rings. That's the theme of working in this direction. I switch over to the topic of algebraic elements. So what is an algebraic element firstly? If you have a commutative ring R, you have an algebra over it, A, and some element belonging to this will be called algebraic if it satisfies a polynomial with coefficients in the ring that you begin with. And the common algebraic elements, in fact, the elements of our interest are nilpotent elements, the idempotents, and the torsion elements. So for these elements, for algebraic elements, if you have an element in the complex group algebra, which is algebraic, and suppose f of x is the polynomial which satisfies it, and lambda is the maximum of the absolute values of the complex roots of f of x, then this inequality holds. So this epsilon I that you see is partial augmentation. I stands for the ith conjugacy class, and kappa I here in the denominator is the conjugacy class. It's denoted by kappa I, and the modulus in the denominator means the size of conjugacy class, and in the numerator it becomes the modulus, the value, absolute value of this complex number. And so a fairly natural function of the coefficients of an algebraic element in complex group algebra is bounded in terms of the complex roots of the polynomial which is satisfying it, right? And this inequality was first proved in 1990 for finite groups. which was comparatively easy to prove. Subsequently, in the same year itself, Passi along with Passman proved this inequality for arbitrary groups. And this was obtained by embedding by using embedding of CG in a Hilbert space H and then considering the uniform closure of CG in C star algebra of bounded operators on H. This was extended to include finite matrix group rings, and some well-known results about group rings were seen as a simple consequence of this inequality. So what shape does it take on the matrix group algebras is here on the slide. So if you read a matrix group algebra MNCG as group ring where the group is MNC, then an element of it which looks somewhat like how it is expressed there, the matrix coefficients are there. And if you define partial augmentation to be taking sum of the traces of the coefficients involved, the coefficients here are the matrices. And if lambda is maximum of the absolute values of roots of this minimal polynomial mx of A, which you begin with, then you have a similar inequality falling for this. As a consequence, I quote two results which were obtained as a consequence of the inequality which we saw just now. So for a finite abelian group, every torsion unit A, which is identity modulo the augmentation ideal, that is similar in M2CG to a diagonal matrix with group elements on diagonal. And so that shows with this equivalence, it's it's easier to study these algebraic elements. And then contributing to Zassenhaus conjecture, there is something very relevant which comes here. If G is an abelian group having an abelian subgroup of index 2, then every torsion unit of augmentation 1 in ZG is rationally conjugate to an element of G. So Zassenhaus conjecture holds for torsion units in ZG if G has an abelian subgroup of index 2. That G abelian in starting should be missing, I guess. There's some mistake. All right. So I move on to the next part which is about the Jordan decomposition property. The Jordan decomposition of matrices is a very familiar concept. This was translated or this was seen in terms of elements of group algebra. So what is it? Let's first see this thing. I'm sorry, there's a slide which has gone over. Okay. So if you have a field of characteristics 0, A is a finite dimensional F algebra, then an element in that algebra can uniquely be written as a sum of semisimple element and as a and nilpotent element. These two components do belong to QG, right? So if you begin with an element in ZG and these two components, I'm sorry, I shouldn't be saying QG and ZG. So in the order that we begin with, I'm sorry. So I'll just go over this again. So if you have an algebra, you can write an element of algebra as a sum of semisimple element and a nilpotent element. Now if you consider an integrally closed subring of F, and then you consider an R order in that, and if for every element of that order, these two components also belong to that order, then you say that A has additive Jordan decomposition. For example, if the common order that we have seen all these days are like one is ZG, integral group ring in QG. So if you begin with an element in QG, you write it as some of these elements, semisimple and nilpotent, and both these components happen to be in ZG again, then you say that it has AJD, that's for additive Jordan decomposition. Then the concept of multiplicative Jordan decomposition. Similarly, if you have a unit element in the order, then you can write it as product of a semisimple element and a unipotent element. And if these two components happen to be in A again, then you say that this has MJD, the multiplicative Jordan decomposition. It's not difficult to see that additive Jordan decomposition implies multiplicative Jordan decomposition, and equivalence holds if it holds for every element in the unit group of A. All right, so when this Jordan decomposition property is seen for the rings, for the orders that we are generally interested in, that is matrices over ring R or group ring RG, then what is the situation? Here are the few results which are listed in this direction. If R is an integral domain which is integrally closed in its quotient field f of characteristic 0, then AGD, additive Jordan decomposition, holds in M1R, M2R, but fails in MNR for n greater than equal to 3. Similar result we have for multiplicative Jordan decomposition as well. And not only this, it puts a restriction on the components that can occur as the Wedderburn simple components, right? So if a group is such that AGD holds in its integral group ring, then it gives you a bound on the dimension that can occur. So Ni is less than equal to 2 if additive Jordan decomposition holds, and it is bounded by 3 in case multiplicative Jordan decomposition holds. So in series of paper on Jordan decomposition in the integral group ring, one gets a list of groups for which either of these properties or both of these properties hold, and where it does not. Here is the complete classification of the groups for which additive Jordan decomposition holds. I'm not going over the list, it's just to list few examples. You'll get number of examples if you go through the papers. Here are some of them. And then for two groups for which integral group ring has multiplicative Jordan decomposition, we have a complete answer, right? So here this is for groups of order 2, 4, 8, 16, 32, and then it's generalized for groups of order, I mean all two groups it has been known what is the situation. Then there's another work which puts a restriction on finite groups which have multiplication Jordan decomposition, and this is quite a restriction which is put on these groups given in group theoretic terms. The work on Jordan decomposition in group rings initiated almost 3 decades ago and is still active. Numerous research papers and survey articles contribute to this direction of work. I then move onward to talking about the structure of semi-simple group algebras. This is not a trivial work, but I've just put it in one slide to kind of give an overview what has been done in these. In series of articles, the object of investigation has been structure of group algebras, may it be finite group algebra or rational group algebra. So we have seen this thing in earlier talks that one of the fundamental questions in this direction is to find a complete set of primitive central idempotents and then to find out the simple components associated. For rational group algebra, a complete set for a class of finite groups, a complete set of PCIs as well as explicit expression for them as a group ring element was given in his papers, and this led to the complete description of the structure of this rational group algebra. For finite group algebra, similar work was done for the class of metabelian groups, and in addition, the group of automorphisms of these group algebras was also described. On the unit groups of group rings, so we have seen already that the structure of QG has a structure of rational group algebra has its implication on the unit group of integral group ring. That's not the only way to study it, but that has impact there. So he studied about the hyperbolic unit groups. When is the unit group of integral group ring hyperbolic? So here is the result. Here is the main result that I would like to quote. If G is a finite non-Hamiltonian group, then all these are equivalent statements. Exactly one Vidurban component of rational group algebra is M to Q, and any other component is either field of rationals or an imaginary quadratic extension of Q. So that gives you quite a restriction on what are the components that you get in case you have a finite non-Hamiltonian group. Then G has a normal free complement, which in itself is a object of investigation. This unit group, so U1 means augmentation 1 units. U1 is virtually free, or saying that U1 is hyperbolic. All these are equivalent statements. Not only this, if a torsion group embeds inside a hyperbolic unit group, then G must be precisely one of these classes of groups which is listed over here, and all of these do have hyperbolic unit groups. I'll quote another result here, which says that any infinite polycyclic by finite group G which embeds into group G whose unit group is hyperbolic has to be satisfying one of these following properties. That is, so here are the properties: that the torsion elements should form a subgroup of G, G should be of this structure, or the unit group, the whole of unit group should be same as the torsion group of G. So these are the properties that revolve around understanding when is the group of units of integral group ring hyperbolic. And going beyond integral group ring, he has also contributed for this field, which is quadratic extension of rationals. The result says that if you work with this K, which is which is quadratic extension of rationals, then unit group of OK is the ring of algebraic integers of K. So if you work with this group ring, then there is restriction on the choice on the groups and the field that you get. So basically, apart from a few cases with G cyclic, the only candidate is the quaternion group of order 8, and all other cases are ruled out by the fact that hyperbolic group cannot contain a free abelian group of rank greater than or equal to 2. So that is something very useful result that we have here, that a hyperbolic group cannot contain a free group of rank 2 or more, which cuts down the choices for us. Okay, coming on to the last section of the work of Professor Passi on the central units of integral group ring. This is something that we have seen in the previous talk by Andreas, where he presented work on finite cut groups. The word cut comes from central units trivial. I'll go over some of the results, some of them will be repetition, but then these are the things that have been found out while working with these cut groups. A group with cut property must necessarily be divisible by 2 or 3, right? Prime spectrum always contains 2 or 3. A nilpotent group, which is a cut group, is always a 2-3 group. There's a simple criteria, a group theoretic criteria, to check if a given 2 group or 3 group is a cut group or not. And cut property implies normalizer property, which is not a very obvious thing that we have for integral group rings. And then there are only finite number of metacyclic groups up to isomorphism which have this property. And it may be noted that various methods which are developed around study of cut groups, they involve various areas of mathematics, namely group theory, representation theory, algebraic number theory comes into picture, and K-theory as well. So here is the list of those metacyclic groups. All right, extending this notion to arbitrary groups. So that was about finite cut groups. Extending this notion to arbitrary cut groups, we have groups with the RS property. So a group element X satisfies certain condition if it's a cut group, and similar condition we have for the torsion elements in arbitrary group also. We call it an RS element with the name of Ritter and Sehgal, who gave this condition in their work of 2005. And a subgroup of G which has all its elements as RS element, we call such a group as RS subgroup. So in this paper, which was concerning arbitrary cut groups, we examined class of cut groups under extensions, including amalgams and HNN extensions, and provided several interesting examples of infinite cut groups, which were not known earlier. Analogous to the case of metacyclic groups, for the finite case, we also gave classification of infinite metacyclic cut groups. Then we classified P groups and nilpotent groups, which are cut groups. Modulo the trivial units, the group of central units is isomorphic to a torsion-free subgroup of central units of ZG consisting of symmetric central units. And as a result, we have that all central units of integral group ring are trivial if that is true for all symmetric central units. Not only that, the quotient, so this Zi, this denotes ith term of upper central series. So this quotient is of finite exponent provided the center is of finite exponent, or G is generated by torsion elements of bounded exponent. So these are the results that we obtained by studying the properties of an arbitrary cut group. It's very interesting to see that a work on the central series of ZG done in 1993, which states that the central height of integral group ring ZG, sorry, the unit group of integral group ring ZG is at most 2, is used along with the cut property that we have recently studied to describe the upper central series of integral group ring almost completely. So this result says that the central height, that means the point where the nth center is equal to n plus 1th center, that is at most 2. And not only that, this was known when is it exactly equal to 2. The groups were described. Now central height 0 essentially demands a group to be a cut group, okay, with trivial center. That's an additional condition. So classification of cut groups give you the groups with central height 0, and then you know about the central height 2 cases. So what remains is to find out the center of the group ring ZG, unit group of ZG, and that gives you the complete information of upper central series of the integral group ring that you began with. Yeah? All right. And then what about analogous question for the lower central series? Naturally, the very first question which turns out is, when is this unit group nilpotent? This has been completely answered, but this is a rarity. You see that UZG is rarely nilpotent because it usually contains a free group of rank more than 1, right? That's something that we have also seen that we can that one sees while understanding, while describing the structure of this unit group. But then the next obvious question is, okay, fine, if it is not nilpotent, what about its residual nilpotence? That is, because a free group can be residually nilpotent, you can have intersection of all terms of lower central series as trivial, even if it is a free group. So even if free group is present in this group of central units, when do you expect it to be residually nilpotent? So for finite case, a complete answer is known by Musin and I.B.S. That's work of 1982, where they say a finite group is residually nilpotent for a finite group G, UZG is residually nilpotent if and only if it's a nilpotent P abelian group. P abelian means the commutator is a P group. So we have kind of started working in this direction to explore, just 1 minute more, to explore the residual nilpotence of this unit group. And for this, analogous to the dimension subgroups, we define a descending series of subgroups of ZG, which contains all those units U which lie in 1 plus delta n. Delta n is the nth power of the augmentation ideal. So one clearly sees that if you look at the lower central series, the components of lower central series, they are contained in the corresponding nth element of this series. And if I define u omega to be intersection of all these, all the terms in this series, then that being trivial implies U is residually nilpotent. So this is one of the criteria that we can use to see when is U residually nilpotent. So I'll not describe what is infinite P element, but I'll just end with saying something about the result that we have about when is this component U omega trivial, so that in these cases we have that U is residually nilpotent. So if G is a nilpotent group and T is torsion group of it, if TP denotes the set of infinite P height elements in the torsion group, then this happens exactly if and only if G is one of these groups listed over here. That is, it's either a torsion-free nilpotent group, or it's a 2-3 group of exponent 6, or it's a P group but then has no element of infinite P height, or this kind of condition exists that you have an element which gives you the residual nilpotence of U in desired way. All right, and I've listed most of the things about group rings, but as I told earlier, it was not possible to put up everything together. A major contribution of Professor Passi is also towards the application of various homological methods to some classical properties in theory of group rings, and some of it, the glimpse of it, you will be able to see in his own talk, which is tomorrow. He's recently been working on Condel rings as well, about which Professor Bardakov is going to speak about in his talk. Yeah, that's it. And just a little more. So as stated in the beginning of talk, I have my own notions of understanding Professor Passi and his work. I'll take this opportunity to express my feelings for him as a student, as a collaborator, and more than anything, as a fan follower. As I told you, the group ring notion in the beginning that I have for him, that he has always expanding group ring. So here are a few lines I've written for him. His presence has charisma and magnetism that teaches us a lot more than isomorphism, because teaching is not the only virtue. Discipline, humility, and passion, to name a few. Fellowship or award or any prize, he inspires us only to rise and rise and rise. He doesn't pound limits and sets his students free to think of finite or indefinite like a sea. To write or to edit or to review, one thing is clear in his view. Work could be multiplicative or trivial, a note or a book or research article. Excellence is utmost essential. What else could be expected as ideal? To his work, he stays faithful, uses primitive ideas, gets them rational. His research then witnesses augmentation, and this is how induces a new dimension. A person who has touched the greatest heights, yet the tone of his voice is always light. A great person, inspirational researcher, and an ideal teacher. Of course, none other than our Passi sir. Many happy returns of the day, sir.